So there. Sorry about that. Those online, that should work now. There we go. Anyway, all I was announcing was that if you're online, you may not be able to come, but from 4 to 6 p.m. right after this course in the Shore Center is a networking event. You can meet dozens of employers casually in a relaxed environment and have some pizza over there. So head on over there if you're interested. Otherwise, to continue from last time, and today we're going to continue on functions. Wednesday it's going to be an exam review. I'll bring old exams and we'll do as many as we want in that 50-minute period. But otherwise, Friday there's no lecture because of your exam, which opens at 9 a.m. All right. If you have any questions or concerns on how to prepare, if you've done well on all of your hacks up to this point, or have fixed your hacks up to this point, then you should be well prepared for the exam on Friday. Right? Otherwise, last time we went through how functions work. We've got this thing called the call stack, and every time you call a function, a new stack frame is created. And it's called a stack because you only work at one end. You add something to the top of the stack that's called a push operation. When you take something off the top of the stack, that's called a pop operation. And so it's super, super efficient to do this because you're leaving breadcrumbs. How does a function know where to return where it came from? Well, the stack tells the story, right? It's a bunch of breadcrumbs for getting back to where you came from. What I want to do today is revisit and focus on unit testing. Now that we've got modular programming, we can separate our code from our tests. So more formally, what is a unit test? A unit is a piece of code. It's usually a function, but it doesn't have to be, that can be tested. In general, it is an indivisible piece of code. So that's why we usually go with functions. If you do it with a snippet of code with like 5 lines of code, you could take that apart and like test the first 3 lines and then test the second 2 lines. And those would actually be 2 separate units. But by saying that we're going to test all of our functions, we treat them as black boxes. There's this thing that we feed input to, it gets us output, and we don't have to break it open and divide it even further, right? We're going to treat it like a black box that you just have input and output, so that you test it in isolation, so that you can test it in isolation of all other code. We don't want to have to rely on the fact, well, that code broke because of that code over there, and that code over there broke because of that code over there. We don't want to have to follow that complex chain. We want to isolate this piece of code. We don't care about the dependencies under the hood, how it operates inside. That's why it's a black box. We just care that it works, that we've got input and output. We keep it simple, right? The KISS principle. A unit test itself, when we test this unit, is an input-output pair that is known to be correct. We know that this is correct from some other means other than our code. We wrote it out on a piece of paper. We pulled out our calculator and mashed the keys until we got the answer. We put it through Wolfram Alpha, right? We have an expected output. We've got an input that should produce that expected output, and then we use that to test our code, right? We unit test by feeding that input, the known correct input, into our unit, into our function, and comparing the result to the known correct output, the actual output versus the expected output. This is exactly how the grader runs, right? The grader is a unit testing framework that displays the expected output, your output, and the graders just simply check to see if they match. If they do match, guess what? It passes, right? If it doesn't match, it fails, right? No S there. There we go. All right. Grouping multiple unit test cases together gives you a test suite. And we like test suites because they are automated and they are repeatable. All right, if we go and make changes to our code and cause a regression, we'll define that in a moment here. We want to be able to run these tests all over again, right, with the click of a button or the run of one single command without having to change this value, compile it, run it, change it again, compile it, run it, do it over and over again as you would with ad hoc testing, right? If a future bug is reported, guess what? We have a new test case. If some user comes back and says, well, this program crashed when I tried it on value 3, right? Ah, there we go. There's an input that we can use. What should happen when we feed 3 into this thing? Should it crash? Probably not. It should produce 2, right? There's our test case. And then we can go back to the drawing board, see, oh yes, indeed it failed. We now have a candidate for debugging this. And debugging is something that we'll look at in the future. A future change to the code may cause unit tests that passed before to now fail. This is known as, this is a regression. It's regression because you're regressing instead of progressing, right? Progress is moving forward. You are making progress and fixing up bugs, fixing code, making it better. A regression means that you've broken something and that you're taking a step backwards. And that's what we call it. It's a regression. Tests should be automated and repeatable. Why? Because we like automating stuff. We don't like doing a lot of work. The more tests you have, the higher certainty you have that your code is correct, assuming that they all pass, of course, right? No matter how many tests you have, you never have a proof, a mathematical proof that your code is correct. It could also always be that, oh, well, we didn't test that situation, right? Or we weren't thinking about that when we designed this. Oops, we need to go back to the drawing board on that, right? And then we add our test, and our test suite improves until we have an even higher certainty, right? This goes into something called the Pareto principle, right? The last 10% is the hardest, right? You can, in any endeavor, 90%, there are different formulations of this, but you can get 90% of it done in like 10% of the time. It's that last 10% that takes 90% of your time, right, in order to get it done. And that's true in a lot of things, right? It's true in like 90% of the causes are caused by 10% of the problems or something like that. It's the Pareto principle that's stated that way in various scenarios and cases. But we want good code coverage, right? The more tests we have, the more assurance that we have that our code is correct, the more code coverage we have. So if we're testing this function that has 5 lines of code, and all of our tests touch these first 3 lines, but none of our tests touch these other 2 lines. Now, without breaking it open, we don't necessarily know that, but we want code coverage. We want more tests. We want as many tests as we can. We want to test corner cases. We want to test edge cases and extremal cases. Right? What happens when we test it? What happens when x is 0, right? And we end up dividing by 0? We need to test that. What happens on the 366th day of a leap year? Right? That's an edge case. That's an extremal case that needs to be tested because that code was never actually executed in any of those tests in that Zune test suite, right? Whether or not there was any test suite at all, right? You could also have randomized testing or fuzzing, right? Randomized, there we go. To try to break your code. Fuzzing is where you just throw everything at your code to try to get it to break. And the second that it does break, oh, okay, there. Now we need to investigate that further, right? And you can randomize this stuff. In fact, later on when you run the grader, we've developed randomized test cases. We will test your arrays functions on 1 million arrays that are randomly generated. And it'll come back and say, you failed 200,000 tests, right? Well, that's probably because of one small bug. You fix that one small bug, and now suddenly you're passing 200,000 tests, right? So don't see a message like that and say, oh, I've got 200,000 bugs in here or something like that. No, you probably only have one bug that caused all the problems. Again, the Pareto principle. 90% of the bad things are caused by 10% of the bugs or something, right? Potential problems with testing would, of course, be a lack of code coverage, right? If you only have one test, or if you have 0 tests, it ain't tested. If you have one test, okay, well, that's good, but you need more. 2 tests, okay, that's better. 3 tests, even better. 4 tests. How can we tell you, oh, 1,000 tests? Okay, that's probably enough, right? Where do you stop, right? You stop when you've got decent code coverage, whatever that metric is, right? All right, you can also have what are called false positives. False positives, can't type today. When a test case is wrong, but the code is right. In the test case, false positive is wrong, but the code is correct. There we go. I'll state it like that, right? It says that this test case failed. I look at my code. I don't see where the failure is. There's no bug in that, right? It's only a one-liner, and I'm pretty sure that it's correct. Go back to the test case. It could be that the test case is wrong, right? In which case you have a false positive. You need to fix the test case. So it could be that one or the other is wrong, and that's when they come up with an agreement. A false negative, right? When there is a bug in your program, but your test suite does not indicate it. And that could be because you don't have enough tests there. It could be because, and this is extremely rare, but your code could be wrong and your test case could be wrong. They just agree in how they're wrong, right? And in that case, everything is wrong, right? Even though it says it passes. Well, it passes, but then it gives you garbage results, or it's not conforming to whatever standard or specification that you were given for the actual program, right? So these are all things that you have to be wary of, that you have to be careful of. And this all goes to something called TDD, which is test-driven development. A lot of evangelists in the TDD will say that you always need to write your test cases before you write your code, right? You don't have to be that pedantic about it. You could write them in parallel. You could write the test cases as an afterthought later if you want to, as long as you do them correctly. That you don't use your code to verify that the test cases are correct. As in, I'm not going to use Wolfram Alpha. I'm not going to use a piece of paper to determine what the output should be. I'm going to use my program to determine what the output should be, right? And then I feed that back in my program, and I miraculously claim that I've got a 100% isolation. If it's done before, during, or after, that's up to you, right? But that's all goes to test-driven development. That generally, you write your tests before the code. Right? It can also be helpful in a lot of ways if you write your tests before your code, because it informs what your code should look like, right? This is the behavior that I expect of my code. Well, then that informs how you design and implement your code. I instead take the personal philosophy of testing as the M.C. Escher painting, the hand drawing the hand. M.C. Escher. There we go. Hand drawing hand. I don't know what it's called. Images. There we go. But, this one hand draws the other hand, right? So the tests inform your implementation inform your tests, and it's this never-ending dependency on each other. And that's the view that I take as far as testing goes, okay? So what we're going to do today with the rest of our time is I'm going to give you a demonstration of an informal unit test testing in C, okay? Later, this is like Lab 6, Hack 6, you will use a more formal unit testing framework called C-Maka. C, of course, stands for the C programming language. Maka is short for mocking, right? You mock data to test data, fake data, so that you can test it to see if it works. That's where it gets its name from. There are a couple of dozen different unit testing frameworks for C for pretty much any language. Some of them are built into the language. This one is not. This one is actually derived from a Google project that Google always abandons their projects. They abandoned a project, I think it was originally called C Mockery, and then somebody took it up and said, okay, we'll rebrand it and we'll continue it. And it is a popular, I don't know if it's the most popular unit testing framework or not, but it's the one that we'll use for this course. More on that later in a couple of weeks. But what I want to do is I want to do informal unit testing, okay? What that means is I'm going to create a file to test my other code. The code that we've already written. Is this big enough? A little bit bigger. There we go. The code that we've written for financial stuff. Get monthly payment, round to cents. I want to test both of these things. So what I'm going to do is I'm going to come over here, and I'm going to start writing code to test my other code. Now, we've done this already. When I opened up a demo and then put values into it, and I printed them out to the screen, great. Looks like it works to me. That was ad hoc testing because it was not repeatable. Right? I erased that code, I threw it away, or I had to go back and change the values, compile, run it again, and visually verify that it was correct. I want to automate that process now. Okay? Let's go ahead and test the get monthly payment. Right? Because I've got those numbers memorized in my head right now. I'm going to write a test to see if get monthly payment is correct. Right? So what I need is some input. So what are my inputs to get monthly payment? The annual rate, the principal, and the years. Right? So the double annual rate, principal, and years. Right? And give me one test case here. Annual rate, what was it? I think 5%. Right? This is the one that we were using before. Principal was, I think, $10,000. Right? And years was 5 years. Right? Okay. What's my expected output? Do we remember that? Off the top of my head, I think it was $188.71. Oops, 71 cents. Right? Whatever that was. I don't have it up. I don't have it brought up, but you can. I'm pretty sure that that's correct, and I'm going to cross my fingers on it. Right? What is the actual output? Right? For that, I need to actually call my function. Right? The function was called get monthly payment. There we go. And I will give it an annual rate, principal, and years. Now I need to compare the expected output with the actual output. If they're the same, then it passes. So if expected output is equal to the actual output, then I say that it passes. Printf passed. There we go. End the line. Otherwise, if they don't match, what should I output? Failed. And we'll go with failed because both of them have 6 letters in a monotype font. Right? They line up nicely. Right? Pass, 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 failed, failed, failed. I should also probably print out some additional information here. For example, printf, I'll say that I'm testing get monthly payment on the following inputs, %f, 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 right? Dot, dot, dot. On the annual rate, the principal, and the years. Just to inform myself of what am I actually testing here, okay? Now, let's see if it passed or failed. I don't know. So first of all, what do I need to do if I'm going to bring in that function over here? I need to, if I'm going to test the math function, what would I do? Include the math library. If I'm going to test my finance functions, what should I include? Include the financial.h file. Remember why I used double quotes there? Because it's a user-defined library, and I'm telling the compiler, don't look in the standard spot, look right here in this current directory. Right? Is that going to compile? I named my file finance tests. Yep. Oh, thank you. Financial. There we go. Still not going to compile for other reasons, though. Oh, finance. There. Okay. Finance. There we go. Sorry. I thought it was financial. Still not going to compile for other reasons, though. Right? Why? When you compile with a math library, what do you do to bring it in, to link it in? -lm. What's the equivalent of -lm here? Include that object file. Do you remember that this was an entire process, right? That we have to compile that finance.c with a -c flag first, which produces a finance.o object file here. Once we've got that, we can go ahead and compile everything together using the O file, the mains.c file, and then the -lm flag here. All right, type. GCC C finance.c. Great. That produces a finance.o file, which should now be over here. Where is it? Right there. Right. Now I can bring everything together. What is it? Finance tests, finance.o, and -lm. And that produces an a.out file that I can now run. Right. Testing. It passed. Right. Great. I'm reasonably sure that this is working. Right. One test, is that enough? Nope. I also don't. Okay, fine. I'm going to go ahead and make some more tests here, but I don't like typing. Right. I don't like typing to GCC, the finance.c, GCC, all this stuff together, et cetera, et cetera. What was the tool that we briefly looked at on Friday to relieve us of the need of doing this? Makefile. Right. Let's go ahead and now define rules for building our testing. Right. So what was that called? Finance tester. Finance.o. It depends on the finance.o file. It depends on the finance tests.c file. How do you build it? Same way that I build this other stuff up here, but instead of loan, it will be finance tests. Tests? Yeah, tests. All right. .c. And I want to build my finance tester program. There we go. Now all I have to do is what? Type one command, make. Now, do you see a finance tester program over here yet? I see an a.out, but I don't see a finance tester program here. So what happens is it ends up building the first thing that it finds. Right? Just like an if-else-if condition, the first one that's true is the one that gets executed. If you have another rule down here of something else to build, you have to provide another make command. Make the finance tester. Right? Tester. There we go. And it made that. And come on, finance tester. There it is now. And now I can run that just like I would run an a.out file. Finance tester. There. And it still passed. The advantage here is I do not have to retype everything every time I make a change. Let me go ahead and add another test over here. Let's see. Copy. Paste. I need this stuff too. What if instead of 5% we had, I don't know, 2.5% instead? Right? Same $10,000, 5 years, whatever. I have no idea what the expected output is now. How would I know? How should I go about finding out that out? Take out a piece of paper, write it down, pull out your calculator, mash the keys, pull out Wolfram Alpha, and use that. Use it to determine the monthly payment or whatever it is. Right? Or you can even find monthly loan payment calculator online or something. Payment calculator. Hey. Loan amount, $10,000, 5 years. What is it? What did I say? 2.5? Calculate. $177.47. Cool. Somebody else said that. I don't know if it's correct or not. We'll find out here. Right? This is not going to compile because I already have declared these, so I'm going to remove that, and I'm going to remove that. There we go. And I made a change. Do I have to type all that stuff again? Nope. Just make finance tester. Run finance tester. And they both pass now. Wonderful. Right? Now I've got my framework here. I can go ahead and cut and paste this chunk of code here over and over and over again and get as many tests as I want. Right? Suppose that we've got an annual rate of, I don't know, 7% now instead. It's definitely not going to be $177.47. This test is going to fail. And let's see what it looks like when it does fail. Right? It just says failed. I'd like some more statistics run out of this, right? If I had 100 test cases, I'd have to go through and say, all right, pass, pass, pass. It looks like they all pass. And then I would miss that one fail. Right? What if I had some statistics. Right? For example, the number of passed, right, and the number failed. I'll start those both out at 0. Indent at the same level. There we go. Semicolon. There we go. Now, every time I pass, what should I do? Increment. Num passed plus plus. If I pass another test, num passed plus plus. Every time I fail, num failed, or yeah, failed plus plus. Put num failed. Yeah, I did num passed, num failed, so that I would have exactly the same number of characters, so there would be no guesswork here. Num failed, num failed, num passed, num passed. There we go. And then down below, I could report the overall statistics. Printf ran %d tests dot dot dot, and the line. How many tests did I actually run? Int total is equal to num passed plus num failed. Right? That's how many total tests I ran. You can report how many total passed. Printf passed %d and the line. Num passed. You can report how many failed. Oh, got to spell passed correct. Passed, fast, failed, failed. There we go. And then what would be a nice thing to include at the very end? What feels good? What kind of grade feels great? 100%, right? Percent. Well, we just want to go for an A. We want to go for 100%, right? Percent, F. How do I get a percent sign? 2%. Percent, 2%. And the line. Right? And how will I get the number that I passed as a percentage? The num passed divided by the total. Careful. That's going to be an integer divided by an integer. What happens? Truncation. So what do? Double one of them. And it will be on the scale of 0 to 1, 50% being 0.5. I don't like reporting it like that. This is for a human user, right? So multiply it by 100 so that you get 0 to 100 instead. Do I have to compile? Nope. I just have to go make again. Done. And run it. Done. Num passed 2, num failed 1. 66%. And again, this is not passing because I have no idea what this should be. We could again go over here for 7% instead. Calculate that. 198.01. Come back over here. And 198.01. Our test case was wrong. It was a false negative. Oops. Make, run. Now we're passing 100%. Cut, paste, cut, paste. Except that what's even better than cut, paste, cut, paste, cut, paste? Put that into a function. A function that tests your other function. What's even better than cut, paste, or write a function and then cut, paste that function? Use a library. And that's what you'll be doing in week 7. You'll be using CMaka that does all of this stuff for you. It does all of this boilerplate stuff of printing stuff out, of gathering all the statistics, et cetera, et cetera. All you have to do is use it. Now, it is quite complicated, so you could spend hours and upon hours of reading the documentation to figure out how it's done. Don't worry, we did that for you. We wrote an example, we give it to you. You just have to add test cases using that same syntax. Right? All right. Any questions on this so far? No? All right, that's not the only thing that we want to test. What else do we want to test to make sure it works? What's the other function in our library? Round descents. All right. I also don't have a good code coverage here with respect to get monthly payment. What if I did something like this? Let's see. Negative $10,000. I wonder what would happen over here if I input negative $10,000. Want to take bets? Please provide a positive amount, right? It does some error checking here. How would we end up doing error checking over here? That's a topic for after the exam. We have to start doing our own error handling. To do that, we need pointers to free up the return value. Don't worry about it yet, but keep it in the back of your mind because error handling is also part of functions and function testing. Otherwise, I'll just leave that for now. But let's test the other one, the round descents. Right? So let's come over here. I want to test round descents. Expected output. Well, here's what's my input. Double x is equal to 1234.567. So if I round to the nearest cent on that, what should I expect? Should be 1234.57. Right? What's the actual output here? Well, the actual output I'll be calling that round to cents function, round to cents of x. And then again, boilerplate, cut and paste, cut and paste. Use a library, right? If the expected output is equal to the actual output, passes. Otherwise, I am testing the round to cents function here on the input x. Right? Once again, make, run it. Pass. I was really hoping it would fail. Right. Can I get this to break? I really want this to break. Let's try this. 49999999999. All right. I'm trying to get this to break. Maybe not that. No. Let's try to get it to break. What should this be? 0.56. Okay. Let's see if that passes or not. Oops. Not G. Make. There we go. Oops. I can't redeclare X. Now it'll run. Please break. Yes, I got it to break. Excellent. So our expected output is correct. So we've got a faulty test case here. Either our code is incorrect or the test case is incorrect. Or something else is going on entirely. So let's take a look at the test case. 1, 2, 3, 4, 5, 6, 4, 9, 9, 9, 9. That should round down, right? And I agree with you. 1, 2, 3, 4, 56. That should be it. Do we have any information from this output telling us how it failed? Nope. So let's do that. If it fails, let's output some additional information here. Printf. I'm going to tab over so that you can associate it with the failed, right? And we'll say that the expected value is %f, actual value is %f, end the line. The expected output and the actual output. So in other words, we're giving out more information now than we were giving before. Upon a failure, if it passes, we don't want any more information. It passed, great, move on. But if it fails, I want more information. There's the expected value, which matches what our expectation was. But here's the actual value. It rounded up for some reason. Right? And the reason being is that 4999999. So think to mathematics. If I were to write something like this, let me jump down here, go into math mode, and if I go 0.999999, if I do an overline, I'll just do 3 nines. Right. Now go back to grade school. What does that mean? Forever. That repeats 9999999 forever. Now put on your calculus hats and tell me, is there a difference between that versus 1? Nope. Right? Those are exactly the same. Right? Infinitesimally out 99999 is the same as 1, right? As far as calc is concerned. As far as computers are concerned, same story here, right? If I just look at 49999999999, guess what? That's 5, right? And so that's why I thought I would end up successfully breaking this. So what's the solution? Change our expectations? Yeah. Or change the input values. Yeah. Or we can build in a little bit of tolerance. If it's off by a penny, who cares? Now, this is not the same story in the grader, right? We want you to be on the dot, on the penny, because we want you to round to cents correctly, right? And if you use the code that we've been giving you, you will round to cents correctly. Right? But if I want to tolerate just a little tiny bit of tolerance, maybe I can tolerate like 1 cent. Double tolerance is equal to 0.01. Right? Now, instead of writing this code that they have to be exactly the same, I can write a little bit looser. If the expected output and actual output are off by less than tolerance, pass, ... How can I rewrite my if statement to capture that? I no longer use the equals equals. If I were dealing with integers, by the way, equals equals is what you want because integers are dead on. 5 is not the same thing as 4 in mathematics, in computer science, ever. Right? These two things are never the same. But 0.999999 forever and 1, those are the same things in mathematics and sometimes in computer science. So I want to build in a little bit of tolerance here. What if I took their difference? The difference between them. If their difference is smaller than the tolerance, then it passes. You've got to be careful, though. What if one is large and the other is small, versus one is small and the other is large? Right? One of them might be negative values, right? The small minus the large, that's going to be a negative, right? Which is still fine. It's just magnitude is small. How could I look at just the absolute value between them? Use the math library. If the absolute value between them is small, then you're good. Now tell me about abs. What are abs good for? Integers, right? So what should I be using here? Fabs. Fabulous abs. Right? Then they're good for crunches. But anyway, there we go. It passes. Let's see if it passes now with our tolerance. Oops. Semicolon. Fine. Make finance tester, run it, and great, we're back to 100% test case passes. All right, any questions on this? Otherwise, this is kind of what we did in Lab 3 with the leap year, right? We gave you this framework, and we expected you to simply cut and paste, and add to it so that you had 6 passing test cases instead. Is it ever a good thing that test cases fail? No, right? Again, computer science, computer software development, software engineering, computer engineering, these are disciplines where if you're off by 1 bolt, the bridge is going to collapse, right? If you can build an entire bridge with thousands and millions of bolts, and if you miss one of them, it ain't going to collapse. But if you write code with thousands or millions of lines of code and you forget 1 semicolon somewhere, it does collapse. If you forget 1 colon, it collapses, right? We don't use colons here, but some programming languages do. So you've got to be careful. Yeah?
So when we turn, if it wants us to use test cases, what do we do with them when we turn them in? Because we can't.
Only if you're directed to. So this is like if you want to test it on your own, this is what I would do, right? And then the finance test.c, you don't hand that in.
Should we like comment them out so you can see them, or just?
No. I mean, it's in a separate file. You just don't hand it in, right? Generally, you want to separate your artifacts. You want to separate your tests and your code, and then when it gets pushed out to production machine, your tests don't go with it, right? Yeah, that goes into something called continuous integration, CI, where you code something, you make sure that it passes all your tests, you check it in as a commit to your repository, then eventually that gets pushed out to production, or hopefully it gets pushed out to a testing environment, and then another testing environment, and then to production or something like that. And that entire process, that loop, is a continuous integration process. Many organizations will not even allow you to commit your code until all tests have passed. Right? So you didn't you broke something. We're not even going to let you look at your code. Go back, fix it. We're not even going to give you the time of day, right? Until that's fixed, until you're passing all the test cases. What you should not do is, again, run it and say, okay, well, the answer was $188.71. It was failing there with 73 because it should have been 71. Okay, I'll go ahead and change 71. Right? That's cheating. Right? That's intentionally making a false positive. Right? But when you're asked to do test cases, I would do it like this just to get in the habit of it. And just not turn it in. If you want to continue the pen and paper method, continue the Wolfram Alpha method of ad hoc testing, only in assignment or like lab 5 and 6, lab 5, hack 5, you actually have to do this. But we give you some starter code to do that. And then in 6, lab 6 and hack 6, you're using CMACA. And we give you starter code to do that. Right? So any questions? No? All right. Well, in about, again, 40 minutes or 50 minutes, I guess, you've got some pizza over in the Ashore Center. Wednesday, we've got our review. Friday is your first exam. So good luck.